This is a pretty simple and easy to build live YouTube subscriber counter. It's currently showing the clearly impressive subscriber count from my channel. It's powered by a 5-volt USB power supply. This is a little battery I got at a conference earlier in the year. Power comes in here into a Node MCU microcontroller. This has onboard Wi-Fi, 4 megs of storage, 128K memory, and it can run either Lua scripts or C++ programs. It's got 9 pins which can be used for output, all of which I'm using here. The first 7 pins connected to the green wires drive an individual 7-segment display at a time. So pins 1, 2, 3, 4, 5, 6, 7, and the dot is 8, which I'm not using. These are all wired together with the blue wires, and the final 2 pins with the white wires are going into this chip, a 74LS139 demultiplexer, which, as I'll explain as we're building this, allows us to enable a single 7-segment display at a time. And you can see these 4 red wires are going into the enable pins of the LED displays. Here are the Node MCU microcontrollers as they were delivered. I bought a bunch at the same time for less than $4 a piece. They're pretty sturdy little boards. You can power them directly from a USB port on your computer. There's a little blue LED which flashes when you upload a program. Here I'm uploading a simple C++ Blink program using the Arduino IDE, and it takes a few seconds to upload. And now it's running. You can see that the LED turns on for a second and turns off for 2 seconds. I also bought a box of these breadboards. They were a few dollars each too. With a little coaxing, the board snaps right in. I used a multimeter to see if any of the pins were blinking, like the tiny onboard blue LED. It turns out that the first pin, pin 0, was the inverse of the onboard flashing LED. So when the LED was off, pin 0 was 3 volts. When the LED was on, it was 0 volts. I then connected ground to the blue rail and then plugged a red LED directly from pin 0 to ground, and it lit up. These 7-segment LED displays are about 25 cents each. These ones are common cathode, which means that they are enabled by connecting their enable pin to ground. They have 10 pins, 5 on each side. 8 pins drive the individual LEDs, and there is an enable pin on both sides. And they also snap right into the board. So the middle pin is for enabling the display. You connect it to ground to enable it. I took a jumper cable from pin 0 and connected it to the various LED segments which made them flash. The next thing I did was to hook up 7 output pins from the microcontroller to the 7-segment display pins so that we could display a figure 8. I modified the blink program to make the first 7 output pins blink. Here you can see the setup function, which is called first. We're setting 9 pins D0 to D8 to output mode so that we can write to them. After setup is executed, the loop function is called over and over. Here we're writing to the output pins, first all lows, then we delay for a second, then we write all highs, and then we delay for another 2 seconds. I've around 450 subscribers at the moment, but maybe I'll reach 1,000 at some point, so I really need to display 4 digits. This presents a little challenge though. We've used up almost all of the available output pins on the microcontroller just driving the first digit. One solution is to share the 7 output pins which are currently driving the first LED display. We can connect those pins to the other LED displays and they will all display the same number at the same time. Here I've shared the pin for the top segment with the second and third LED displays. If we did this for all the other pins, we'd see a flashing 8888. So if we had a way to just enable a single LED display at a time and quickly cycle through which digit we're displaying and which display is active, we could reuse those 7 pins to drive the 4 LED displays. And we can achieve exactly that using this demultiplexer chip, the 74LS139. Here's the datasheet. We're using the top half of the chip. P16 takes a voltage, P15 is enable, so we tie to low to enable for this chip. Then there are 2 selects, A2 and B2, and 4 outputs, Y0, Y1, Y2 and Y3. Looking at the truth table below, you can see that if we give in 2 lows, we'll get a low on the first output and highs on the rest. If we pass in a low and a high, we'll get a single low on the second output. So we can essentially input a count from 0 to 3 in binary using the 2 input pins and get 4 outputs, one of which is low at any time. If we then tie these 4 outputs to the enable pins of our 4 LED displays, only one will display at a time, which is really what we want. So I removed everything but the microcontroller and the demultiplexer from the breadboard. As we're not using the pins on the top, I moved the board up one to give us a little more room below where we will be using. Then there's a few things that I needed to wire up. The bottom pins includes a 3-volt pin and a ground pin, and we'll use these 2 to power the rest of the board. So I then connected the power and the ground to the demultiplexer, and to enable it we tie its pin 15 at the top to ground. The last 4 pins at the top are the outputs, and to test them I connected 4 LEDs. There are then 2 inputs to the left of those. If I send in two lows, the first output goes low while the rest are high. If I try the other three input combinations, you can see that one of the four outputs at a time goes low. I modified the program to count from 0 to 3 in binary on output pins 7 and 8, pausing a second in between. Pins 7 and 8 are here on the board, and I connected the two multiplexer inputs to them. You can see that one of the four multiplexer outputs are now low at a time, and it's changing every second. I then snapped in the four 7-segment displays and removed their plastic covers. The four outputs that are currently driving the LEDs connect to the enable lines of the 4-segment displays. As these are common cathode displays, they are enabled with a low, so at any one time only a single display will be enabled. I connected the remaining enable pins on the segment displays to the remaining outputs of the multiplexer, and then enabled a segment on each by tying them to high. The displays don't have to show the same value, and to mimic this I enabled different segments on each display. To achieve the illusion of all four displays being active at once, we have to reduce the 1 second delay. I first tried to reduce it to 10 milliseconds, but that wasn't enough, as you can still see them flashing on and off. I lowered the delay further to 4 milliseconds, which was much better. They now appear like they're all enabled at the same time. The last thing I needed to do on the board was to hook up the 7 microcontroller output pins to the segment displays. I moved the enable lines to the top so they wouldn't be blocking the displays. And then I connected the 7 outputs to the first display so that it displayed a figure 8. I then connected those 7 outputs to the second display, and then to the third and to the fourth. At this point we've completed the wiring for the board. I used jumper wires too when building the first version below, but when I got it working I then replaced the jumper at a time with a cut to length piece of wire. It took about an hour or so, but the end result is obviously way better. To demonstrate that the board can display a number other than 888, I modified the program to output 1234. Like before, we're writing a single digit at a time, this time with a delay of 400 milliseconds. I added a write digit function which takes a single digit and writes it to the LED displays. It simply enables and disables the appropriate pins which are hooked up to the 7 segment displays. So 0, for example, sets all the pins high except for the middle pin. The digit 8 sets all pins high. If I temporarily enable all 4 segments, you can see how we're sending the same number to all displays at any given time. It's the demultiplexer which allows us to synchronize a single digit to a single display. Here's 1, 2, 3, 4 being outputted with a delay of 4 milliseconds. And here's the board displaying my channel's live subscriber count. The code for this is pretty simple. I'm using some open source libraries which I'll link in the description. We define some constants, first the reader name and password, then your Google API key and YouTube channel. This is my channel ID, but you can swap that for your own one. The milliseconds between API requests is the delay between updating the count. I've set it to 10 seconds. Digit delay is the number of milliseconds between switching LED displays. In the setup function, we set the mode of a bunch of pins to output and then connect to the Wi-Fi, waiting until the connection has been made. Once it has, we output some debugging info to the serial output. The loop function does a little bookkeeping to create a delay between YouTube API requests. If the last request at that time is more than 10 seconds ago, we will make another request. API.getChannel statistics gets the stats for a channel by ID. We output some of the response data to the serial output and then grab the subscriber count to display on the LED displays. And call write subscriber count with this value. Write subscriber count takes a count as an argument. As we did in earlier examples, we count from 0 to 3 on the pins connected to the demultiplexer inputs. We take the subscriber count, divide by 1000 and get the modulus of 10 to get the most significant digit. I've less than 1000 subscribers, so this number is 0 and we just show blank. We delay for 4 milliseconds and then write the second digit from the left, the one that displays hundreds. We do a similar calculation to the first digit and then write it. We then delay for a further 4 milliseconds and repeat for the third digits and then the fourth. We saw the write digit function before. It takes a single digit and sets the appropriate output pins high or low. And that's it. Thanks for watching.